Okay, so this is called Discontinuities in Rational Functions. It's a 0-point lesson because it is a review. All right, so we're going to review some things about rationals that you would have done in Algebra 2. Pretty sure you also do them in Algebra 3 if you took Algebra 3, but either way, definitely in Algebra 2. So discontinuities. Here's what I want you to remember, is that polynomial functions have a domain of negative infinity to infinity, and they're just like wiggly worms all over the place. Totally continuous. You can put your pencil down, draw the entire thing without picking your pencil up. But most rationals have discontinuities, and there's different kinds. We can have some asymptotes, not asymptotes, right? Asymptotes. And in this graph here, we have vertical and horizontal asymptotes. You may be under the false impression or have even been told before that an asymptote is a line that a graph cannot cross, and that is a lie. Okay? You can absolutely cross some asymptotes. Now, vertical asymptotes, you can't cross them. Okay? Vertical asymptotes, they affect the domain. So let's say this was at, let's say that these are at -2 and 2, wherever they are. Then that means x cannot equal -2. So if I crossed over it, then I'd have to have a point where x equaled -2. So it's not going to work. Vertical asymptotes, you will never cross. You are just approaching them from, either going to infinity or negative infinity from one side or the other. Now, horizontal asymptotes, you can intersect, right? So this right here, in this graph in particular, we're not intersecting it. And in most, maybe all of the rational functions you have done up to this point, you didn't intersect it. I mean, that's very much a possibility, but you need to know that you can, because horizontal and slant asymptotes have to do with end behavior. Middle behavior is where it would be intersecting. We don't care about that. We care way out here at the infinities that this function would be approaching whatever that number is on that asymptote. Okay, so let's look at another one. So here's an example of one that intersects the asymptote. So let's say that this is it. Like, you can pretend like my lines are straight. Here, we're not intersecting it. We're just approaching y = 0 from the top. Over here, it does intersect it, but see, it still approaches y = 0 just from the bottom. So I really don't care that it intersected right here, because I'm more worried about what's happening way out there. And either way, it's approaching that asymptote. Okay, does that make sense? Here, it's a function that intersects the asymptote an infinite amount of times. But you can see as the x's get really, really big or really, really small, that the function's going to be approaching 0, which is oscillating or bouncing on either side of it. Here's an example of a slant asymptote. So we have a vertical asymptote here, which we absolutely cannot cross. Slant asymptote, we can. Slant asymptote has to do with end behavior also. Vertical asymptote's more middle behavior because it only affects what's happening right here. But our slant asymptotes, even though it's going up, we're still thinking about when x gets really, really big, that this function is approaching this line. Okay? Here is an example of when we could intersect it. This is not a great picture. I need to do a better one because I know unless you're like right here where I am, it's hard to see this. But this function comes up, it intersects, it actually intersects again, and then it's approaching it from underneath. So this one actually intersects twice. Okay, but again, it could be 2 times, 3 times, an infinite amount of times, whatever. And it could come down like this and do a little wiggle and then still just approach it. And all we care about is the fact that it's approaching it at the ends, right? Not all asymptotes are lines. Here's an example of one that is a parabola. So the function itself is blue, the asymptote is red. So that red is a parabola. It even gives us a little equation here. So it's what we would call a parabolic asymptote. Now, we have to know that they exist. We have to know how to find them, which is really easy. But we're not going to be graphing them or anything like that. But they could be parabolas, they could be cubics, they could really be anything. But if you see like that, because your asymptotes, we sketch them in usually as dotted lines. They don't really exist in there, but they help us get the shape of the graph. You can see that the blue graph is just, it's approaching that right there. And then again, we don't even know this is coming up, whatever else is happening, but then it is approaching that parabola right there. Okay, so those are just some visuals to kind of knock some cobwebs off and get us back into the mindset of rationals. But let's make sure we know what a rational actually is. It's comes, the root word is ratio. If I have 2x plus 3 over 5, that's not a rational function because the denominator doesn't have a variable in it. All right, because it's a ratio of two polynomials. So I need like 2x plus 3. If I put it over 5x, now I have a rational function. Okay, so the denominator has to have an x in it. The numerator does not. If I just have 1 over 5x, that's totally fine. So just really making sure that you have a variable in the denominator will help you make sure that you have a rational function. Okay, that makes sense? All right, so this is going on page 30 when we're done. And this says 0.4a, it should say 0.3. I changed it, it was right, and then I changed it to make it wrong this morning. Was that when I was in a rush because I didn't know I was teaching this today. Is yours right? Oh, and mine is wrong? Oh, good. Oh, look at that. Well, I must have changed it after I put this in here. Actually did something right. Who knows? All right. So most, not all, but most rational functions have restricted domains leading to discontinuities. Probably all of the ones we're going to look at, because they're the interesting, well, they're also kind of interesting, I think, when they don't, because we look at so many that do. But we're going to be looking at the ones with discontinuities. I'll probably show you at least one that falls into the rational category that doesn't have any asymptotes or doesn't have any vertical asymptotes or discontinuities. But asymptotes are not our only kind of discontinuities. All right. What our discontinuities are: vertical asymptotes, horizontal asymptotes, slant asymptotes, and point discontinuities. It's another word for a point discontinuity. A hole. Yes. A hole. Oh no. So point discontinuity. We are going to abbreviate it as PD. They will be referred to as point discontinuities or holes, both of them. But I will probably use point discontinuity more because I think you're more familiar with hole. And you need to just know that they're the same thing. It doesn't matter what you call them, but when you read it, you need to know what they're talking about. Okay. All right, so in order to have a point discontinuity or a hole, they occur when a factor containing x. So if I just factor out 3, we don't care about him. I factor out 3x or something like that, I do care about him. So a factor containing x is common to the numerator and denominator. That means that we can cancel it out. All right, this is why we reviewed factoring. So can I start here by canceling out the x squareds? No, absolutely not. Would Mrs. Archer be very happy that you just said no? Okay, I will make sure she knows. All right, I remember y'all talking about that the other day. I cannot do that because this is, I have addition or subtraction in the denominator. Can only do that for multiplying. So that's a big fat no. But I can factor, right? In the numerator, I can leave this x squared. In the denominator, I can factor out a 3x. That leaves me with x minus 2. Okay. Now I can reduce that. Now, yes, I still have subtraction in the denominator, but do you see how it's in one big term now down there? And I have some multiplication right here. So I can cancel this x with one of those. So what I just canceled out was x. Whatever you cancel out, whether it's x or x plus 3 or whatever, you're going to take that and you're going to set it equal to 0. Then you solve it, which that one solves itself, right? 0. Woohoo, that was hard, right? That is your x value for your hole. So point discontinuity, your x value is 0 because that's what we canceled out and solved. Okay? So now I have a reduced function. My reduced function is f of x equals x over 3 times x minus 2. Okay, everybody with me? That's my reduced one. To find the y value of that hole, I evaluate my reduced function with that x value I just found. So I'm looking for f of 0. That's going to give me 0 over 3 times 0 minus 2, right? Which just gives me 0.
0 minus 2 is negative.
Right, but the numerator is 0, so it doesn't really matter what's happening in the denominator. As long as we don't get 0 over 0, we're fine. If you substituted it back into the original, you'd get 0 over 0, and then that would be bad. Okay? Right, but that's your point discontinuity there. So what that means is this. Your function looks like this. Okay, so your function looks like this, like your reduced form with a hole here. Okay. Well, no, I'm just making sure. You wouldn't have to write all that. You'd probably just have to give me the whole. I just want you to understand what's happening there. Okay. So if you graph this itself, like in Desmos, it'll graph that with a hole. I don't think you can actually see the holes, but if you like click around on it, it'll tell you that it's undefined. Or if you just graph this and then know that your hole's there. So if you're having to graph it by hand, it's probably easier to graph the other one, right? It just depends on what you need to do. Okay. Everybody good so far? All right. So let's look at number 2. Can I cancel out the x squareds? No, I have to factor first. So when I factor, I will get x minus 3 times x plus 2 over x minus 3 times x plus 3. You have to be able to factor accurately and efficiently, right? That is an old skill that you have to have. And if it takes you forever to factor, you can't factor, I don't know what to tell you. So now can I reduce this? Yes, I can cancel those two out. So when I cancel something out that tells me I have a hole, I write down x minus 3 equals 0, x equals 3. That means for my point discontinuity, the x value for the hole is 3. All right, everybody good? Okay. So then my reduced function is x plus 2 over x plus 3. And I need to evaluate that at what? At 3. Good. So I need f of 3 will give me 3 plus 2 over 3 plus 3. And that will give me 5 over 6. What questions do we have? Anything? You have a question? You sure? I don't believe you. Okay. Okay, just look. It's okay to look. It's okay. All right. Can I cancel these 2's out? Or the x's? No. You have to factor. Factor out of 2x leaves me with x minus 3 over 2x. Can I reduce that? Yes. Can cancel those 2x's out right there. So 2x equals 0, which means x equals 0. So for the whole, the x value is 0, right? Then f of x equals x minus 3. Now, if I were to graph this f of x right now, what would that graph look like? It's linear, right? This just graphs a line. You agree with that? This is how you get a line with a hole in it. It doesn't start off looking like a line. It starts off as a rational. You cancel stuff out, you get a hole. That's how you get a line with a hole in it. Okay? So when I do f of 0, that gives me 0 minus 3. I have a hole at 0, negative 3, but a very simple line. Okay. What questions do we have? Anything? We good? Okay. So that's your review of your point discontinuity or your holes. Now we're going to look at vertical asymptotes, which we will use VA to represent. Okay, so vertical asymptotes occur when a factor containing x is unique to the denominator. Here's what that means. Because I was able to cancel these out, this was not unique to the denominator. I got x minus 3 down here. I was able to cancel it out, not unique to the denominator. But this one is unique to the denominator because I can't cancel it out. You with me on that? That's what those words mean. Okay, so that means I have to check for holes first. So if we come across one, even though we're just looking at vertical asymptotes here, we're going to write that stuff down too, because I don't want you to think you can just ignore it if you get a hole. All right. Can I factor anything in number 1? No. Can I cancel the x's out? No. All right. So that means that this is a factor that is unique to the denominator, and we cannot divide by 0, right? That's bad, bad, real bad. So that means that x plus 2 cannot equal 0. That means that x cannot equal negative 2. So my vertical asymptote is at x equals negative 2. That's it. That's very easy. So listen, this is a line, okay? Here, when we made this statement, x equals 3, that's a value of x in an ordered pair. This is the equation of a line, okay? That makes a difference. It's a vertical line. It's an x equals line, right? Because it's representing a vertical asymptote. We good? All right. On number 2, can I start by just taking x minus 7 and setting it equal to 0? No, I have to check for the holes first. So what do I need to do with the numerator? Factor. I got x plus 7 times x minus 7 over x minus 7. Okay, and then we can cancel those out. So that means x minus 7 equals 0, x equals 7. What does this x equals 7 mean? It's the x value of the hole. Very good. So for the point discontinuity, x value is 7. My reduced function is f of x equals x plus 7. So let's go ahead and find the y value over there. So f of 7 equals 7 plus 7. That's 14. Okay. Because I ended up with 1. Like here, there wasn't 1, so I didn't worry about it. But if I ended up with 1, I'm not going to just ignore it because I don't want y'all to get used to just it coming up and you ignoring it. Because if you cancel something out, that means you have that gives you a hole. That's how you know. Yeah. Okay. Good question. What else we got? Anything? Okay. So then we got to talk about vertical asymptotes. If this, y'all stop talking to each other, maybe pay better attention. If I look at this is my reduced function. Do I have a factor that's unique to the denominator? No, because I don't even have a denominator, right? And a line is not going to have a vertical asymptote. So, excuse me. So my answer here is just none. That's a possibility. Okay. Right. Exactly. The one above it, this one has no holes, but it has a vertical asymptote. This one has a hole, but no vertical asymptote. Because not everything has a hole. Not everything has a vertical asymptote, right? Okay. What should I do first in number 3? Factor. It's okay. 2 times x minus 4 over x plus 4 times x minus 4. All right. Can I reduce this? Yes. And since I'm canceling that out, I put x minus 4 equals 0. That means x equals 4. That, because it came from what I canceled out, that's part of my point discontinuity or something, right? My reduced function is 2 over x plus 4. Let's go ahead and finish our point discontinuity. So I need f of 4 is equal to 2 over 4 plus 4. That's 2 over 8, which is what? 1/4. Good. Yeah. All right, so this is my reduced function. This is a factor that's unique to the denominator, so that means that x plus 4 cannot equal 0. So x cannot equal -4, which means I have a vertical asymptote at x equals -4. It's not just -4. It is x equals -4 because it is an equation of a line. We good? What questions do we have? Don't be afraid to ask something. All right. 4 is factored for us. That's really great when that happens. Can I cancel anything out? No. All right. So then that means down here, I have 2 factors unique to the denominator. I have x that can't equal 0, and I have x plus 5 that can't equal 0. So this one takes care of itself, and then x cannot equal -5. So I have 2 vertical asymptotes, which is totally fine. You can have 2, 3, you can have an infinite amount. We'll see some of those. So my vertical asymptotes, they're at x equals 0 and x equals -5. You cannot list them out like solutions. Like if I was solving a quadratic, I could say x equals 0, -5, totally fine. But these are equations of lines, so they're separate, right? 2 different lines. Questions? Easy? We good? Should be, because it's not new, that's for sure. All right, flip it over. There's no PD here because there's nothing I can cancel out. Okie dokie. So now we're going to look at horizontal asymptotes. Horizontal asymptotes are connected to end behavior. So remember, we got all kinds of things going on in the middle. Vertical asymptotes is kind of what I would consider middle behavior, even holes. Okay, but your horizontal asymptotes, they're going out to the infinities, and what we care about is how our function is behaving around that asymptote when we're getting to the infinities. So these occur when the degree of the denominator is greater than or equal to the degree of the numerator. And you have to be able to look at a function and determine if it is top heavy, bottom heavy, or tied in degree. So let's talk about what that means. Here, number 1, the degree of the numerator is 2, the degree of the denominator is 1. That's what makes it top heavy. The degree, it's heavier in the top degree-wise. Bottom heavy, the degree of the numerator is 0, the degree of the denominator is 1, so the denominator degree is bigger. That's what makes it bottom heavy. Tied in degree is when the degrees are the same. Okay? Because if you don't understand what top heavy, bottom heavy, and tied in degree are, none of the rest of it matters. Right? So are we all good on that? Okay. So when a function is top heavy, that indicates no horizontal asymptotes. That opens the door for a slant asymptote, or a parabolic asymptote or something else, but no horizontals. So here, this one is top heavy. So my answer for horizontal asymptote would be none. Just that, none. There aren't any. You don't even have to do any work for these. You just have to know how to recognize stuff. Number 2, is this top heavy, bottom heavy, or tied in degree? Top heavy, so my horizontal asymptote is none. That's it. Okay. All right, bottom heavy, asymptote at y equals 0. And again, it's a line, so you have to put the equation of a line. Number 3 is bottom heavy. So my horizontal asymptotes, y equals 0. There's no figuring it out or solving it. Now, 3 and 4, the equations look completely different, right? The functions are going to look completely different. But the horizontal asymptotes are exactly the same because this one's bottom heavy also. So my horizontal asymptote is y equals 0. Okay? Super simple, but you got to know the rules, right? I mean, it's only as easy as what you know, I guess. All right, so then when we have them tied in degree, that leads to a horizontal asymptote where y equals the ratio of the leading coefficients. So you find the two leading terms, which most of the time should be in the front, but not always. We got to be careful. But these are my two leading terms. So I just make a ratio out of that, and my horizontal asymptote is at y equals 2/5. And it's not 2/5, it's y equals 2/5 because it's the equation of a line. Okay? Does that make sense? All right, so then our horizontal asymptote for 6 would be y equals what? 1. Did you put 2/2? Questions? Anything? All right. Slant asymptotes. Can anybody tell me a different name for slant asymptotes? Okay. They are called oblique, O-B-L-I-Q-U-E. Where are your oblique muscles? No. They're your abs. You know what these abs help you do? Lean over or slant over. Hence the slant asymptotes. Your oblique pyramids in geometry were the leaning ones. It's not a coincidence. It's all tied together, right? That's what oblique means. All right, so your slant asymptotes, those occur when the reduced rational, listen, y'all are awfully squirrely today. Reduced rational, which means you have to find the, you want to find the holes in everything first. Okay, make sure it's completely reduced, and we've looked for all the other stuff first. When a reduced contains an x in the denominator, and the numerator, this is very important, is 1 greater in degree than the denominator. So you know how we put up there when it was top heavy, we have no horizontal asymptote, and it opens the door for slant. It doesn't guarantee, because if it's super top heavy, it's not going to be a slant asymptote. But if it's heavy by just 1 degree, that tells me I'm going to have a slant asymptote. Okay, so the numerator degree is 2, the denominator degree is 1. That's going to give me a slant asymptote. Okay, and we find that by dividing the numerator by the denominator. This is why we practiced long division. Okay, but before I jump into that, I have to look for any point discontinuities. So that means I have to do what first? Factor. So when I factor the numerator, I'm going to get x minus 3 times x minus 1 over x minus 2. All right. And can I reduce anything? No. Okay, so now there's lots of reasons we want it factored. To look for point discontinuity, to help us find our vertical asymptotes if the denominator needed to be factored. In the numerator for us to find our zeros. We'll get to all of that a little bit later. But then when we go to find our slant asymptote, we actually don't want the factor version. So I have this, but I'm going to mark it out because this is what I need. Like I had to try it to see if I could reduce it, but I'm not going to use it. I'm going to use my original. And then I'm going to divide. But you'll like this better, I promise. We're going to take x minus 2, and we're going to divide that into x squared minus 4x plus 3. Okay? So x squared divided by x gives me what? X. And I multiply it back, and I get x squared minus 2x. Then what do I do? Yep, change my signs. Those zero out. I get negative 2x. Bring down my positive 3. Negative 2x divided by x gives me negative 2. And then guess what? I can stop. If we look here, if I continue, will I end up with a remainder? Yes, okay. And if I have a slant asymptote, I will have a remainder. If I don't have a remainder, I either divided wrong or I don't actually have a slant asymptote, okay? But we don't care about the remainder. Now, when we revisit this, whenever our next actual class day is, I will explain to you why. I don't want to explain too much stuff today. It becomes too much. So I'll explain to you what the remainder actually means and why we don't care about it. Right now, we just want to be able to find them, and I can stop there. Because if I kept going, all it would do would be give me the remainder, right? I can look at it and see I'd have one. So I'm done. And it's a coincidence, by the way, I just realized that this is the same as that. Okay, it's a coincidence. So just, it is what it is. But slant asymptote is going to be y equals, because it's the equation of a line, x minus 2. Okay, what questions do you have? Anything? Now, there are reasons that we might need the remainder. That's why we practiced the whole thing, and I didn't tell you to stop on those. It's a skill you need, but we don't have to use it right here. Okay, so on number 2, can I cancel out those 2 x's? No, but I can factor. And I get 2x times x minus 2 over 2x. Now can I cancel these? Yes, I can. I can cancel those out. That means I'm going to have what in my graph? A whole. So 2x equals 0, x equals 0. So since I have a point discontinuity, I'm not going to just ignore it. It's going to be at 0 something. My reduced function is f of x equals x minus 2. So if I find f of 0, that's going to be 0 minus 2, so that's negative 2. Okay. But what I'm really looking for here is my slant asymptote. Well, what is this an equation of? A line. Do I have anything to actually divide? No. Okay. Now here's another thing might blow your mind a little bit, and I will explain it more in the next lesson, not right now. But a line, when you get a line from a rational like this, it is its own slant asymptote. So this is your reduced function, and your slant asymptote is y equals x minus 2. Okay. Only if you just get a line and you can't even divide. Yeah. Okay. Everybody okay with that? Questions? All righty. Now let's look at 3. Can I cancel out the 2 x's? No. Now, let me ask you this. If I were to factor the numerator, would I get anything in the numerator that would cancel out with that 2x? No, because I don't have a GCF of 2 or x, right? If I factor that trinomial, I'd get something like, I don't know what it is, but like 2x minus 3 times x plus 2 or something like that, right? I wouldn't get a 2x unless I had a GCF up there. You with me on that? So since I don't really care about anything else right now, except making sure I reduce if I can, and there's nothing that'll reduce, factoring the numerator would just help us with our zeros, but we haven't even talked about those yet. So I can just start by dividing, okay? So let's divide. I'm going to take 2x and divide it into 2x squared minus 4x plus 3. So 2x squared divided by 2x is just x. So that gives me 2x squared. I change the signs, throw 0 out, bring down my negative 4x, and that'll be a negative 2 there. And for some reason, x minus 2 keeps showing up on here. That is a total coincidence. I probably couldn't do that if I tried, but that's what happened. But I can stop right here, right? And so my slant asymptote is just y equals x minus 2. Okay. Everybody good? Any questions? All right. So I'll just go ahead and be nice and tell you on number 4 that the numerator at least doesn't factor. Actually, the denominator doesn't factor. Neither one of them factor, so we're not going to factor anything. You're just going to divide. So I want you to go ahead and find your slant asymptote on that last one. It's not. Neither one of them are. Neither one of them are. No, I just told you they weren't. My goodness. He doesn't listen. I literally just told you they wouldn't factor. Oh, Charlotte. My goodness. Okay, make sure that you didn't fall into a trap that is very, very common, especially when you're trying to rush through something you think is easy. Did any of you cancel out those 4x squareds? Because that happens a lot. Your brain sees negative 4x squared and positive 4x squared. So if you're not saying, then change the signs on the second row every time, you're likely to just kind of zip past that and make a silly mistake. Okay, so just be very careful. What questions do we have? Anything? We good? Okay, I'll leave that up there for a minute. Those of you that paid attention at the beginning, where's your assignment? Delta Math. Yes, it's in Delta Math. And I don't know if I already said this in here because by 7th period, I've repeated myself a lot. But one of the reasons I made your factoring lesson in Delta Math is because you can always go back to your Delta Math and do more. And so if you feel like you need more practice on factoring different kinds, they're even titled, you can go back and do as many questions as you want, and it's not going to affect your grade. But I don't hide them or anything, so they're always there for you to go back and maybe use them as a review or practice or whatever you need to do. Okay? We good? Awesome.